Welcome everyone. So this is our 87th live stream geometry. We have 3 people here with us now, and I'm going to continue doing more problems from the geometry discussions and problems Discord. So thanks Stefan a lot for showing me this Discord server. I've been using it for a lot of the past sessions, and it has a lot of really great problems. So if you'd like to join us in the future, feel free to email me at mgreenb801@gmail.com. The sessions are every Sunday at 8 a.m. US Central Time. All right, so I'm going to share my screen. Here we go. So here's the first problem. So we have a complete quadrilateral ABCD and any point X. So we have A, B, C, D, and I want to make it so I can see the intersections of those. So BC and AD and AB and CD. So let's see how this looks. Looks like Dhruva might have just gotten kicked off. Okay. So we have this point and this point. Oh, AB, sorry, that should be E, and this should be F. And then we have a point X that's just anywhere. And we draw XE, XB, and XC. Maybe I'll move it like here or something. And we want to see, so XE, we want to see where it intersects AD. And then XB, oh, it's where they all intersect AD? I guess so. So XE, XB, and XC. We want it to intersect, yeah, so let's see, if I do it right here, that looks a little better maybe. So it intersects them at R, P, and Q. So this is R, and then this is P, and this is Q. And let's draw all those circles that they say. So I'm just going to check that the problem's right, and then I will make it look nicer. So EAQ, EDP, and EFR. Yes, so it looks like the problem's right. Okay, so let me make things look nicer. Almost looks kind of like, I don't know if it's a pawn slip point or something, so we'll see. So yeah, I'm going to want to hide a bunch of things. This, 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 and this. All right. This.
I think this is trivial by Desargues, dual Desargues involution theorem.
Oh, really?
I think so.
So not like the isogonal line lemma, but you like apply it a different way?
Not the isogonal line lemma, the full theorem.
The full theorem.
So like what the theorem says. It says that there is an involution at X, which swaps A and C, B and D, and E and F.
Okay, so whenever you have a complete quadrilateral, is that like the case that there's an involution through any point like that?
Yeah.
Okay.
And there is also a thing that you can project involutions through a point. So we basically can project an involution that involution which we know exists by the DDIT through X onto AD. So we know that A and C, they go to A and Q. And so there is an involution swapping A and Q. Similarly, it swaps P and D and R and F.
Okay.
And there is also a theorem that says that any involution on a line is an inversion.
Okay.
And
So
I think, yeah, I think then you can do like some powerful point when you take the center of that inversion and you get that they are coaxial.
okay, so there has to be some point on AD, like
It
maybe
will
a point
be-
right here that inverts all them to each other.
Yeah.
Okay. So G, we could call it like the center of inversion. I don't know if there's a way to construct it.
It is. It will just be like the intersection of radical axes of these circles, which I mean, don't know that exists, but you can at least draw it accurately.
Okay. So the radical axis of these three circles.
Yeah.
It's where the radical axis intersects AD.
Exactly.
Okay. All right. So I'm going to hide this. Okay, so an inversion about here, it sends 8, swaps A and P, swaps D and Q, swaps F and R.
And they also have, so we know that this point H exists and that we have that inversion. And then it is quite easy to see they are coaxial, since we know one point which lies on, which has the same power with respect to each circle. And we also have one point which is the intersection.
But it doesn't seem, okay, so it swaps A and D and then P and Q. Okay, so like it would be a circle like this. Okay.
It swaps P and D and A and Q.
Okay, so it would be something like right here, P and D, A and Q, and F and R. Okay.
Yeah, probably.
Okay. So, and then once we know that, then we'd have a circle that has the same power with respect to all three circles. Or H would have the same power with respect to all three. So it would lie on the radical axis of all three. Okay.
Yeah.
So basically, as long as we're just working in two-dimensional Euclidean geometry, DDIT says that there would always be an inversion, like swapping. So did you say, so it swaps E and F, A and C, and B and D? Is that,
you can't exactly say that an inversion will swap E and F and those in the exact complete quadrilateral, but we can say that after we project the involution on the line. So it is not generally true that every involution is just some inversion, but and this is like a kind of different kind of involution, since this is involution on lines, which DDIT talks about. But those involutions we can project online. And when we do that, then we can know it is an inversion, and we take the center of inversion and like finish it.
Okay, so if you project an involution onto a line, then it has to be an inversion, is what you're saying.
Yeah, involution on a line back to itself is an inversion. That is a theorem, and not actually it is not too hard to prove.
Interesting. Yes, I learned something every day. Yeah, DDIT, that's another thing I have to get better at. Like I know the guy's talking a line lemma, but the more advanced version, I think I3435 solved the problem using DDIT and the Discord. All right. So
I just recently read about it in a Mark BCC handout, and it was quite clearly explained. I think it's quite good.
Okay. All right. So by DDIT, there exists an involution just on the plane, swapping A and C.
It swaps. It is an involution like which swaps lines XA, XC, and
okay, swapping lines XA and XC, lines XB and XD, and lines XE and XF.
yeah.
And then projecting this involution through X onto the line AB. We get a new involution that swaps points A and P, D and Q, or no,
A and Q,
yeah,
D and D,
and Q, P and D, and F and R. And then by a well-known theorem, this involution is an inversion. And thus, its center H is on line AD. Now, once we know that, so then H has the same power with respect to those three circles. So then H has the same power with respect to EAQ, EDP, and EFR, and thus lies on, and thus is their radical center. Okay, so let's think about this. H can be their radical center, but it doesn't necessarily.
It is important that they have a one common point, E.
Okay, so because they all pass through E, then they all have to pass through G. That's right. Okay. E. It doesn't mean that it's the radical center unless they all share a common point. Okay, so yeah. And H is not equal to E, then they are coaxial. So basically, I'll write it this way. So since it has the same power with respect, so it lies on their common, so it lies on their pairwise radical axes. So it lies on all three pairwise radical axes. There we go. All right, this is a really nice one. So once you know this problem shows how powerful DDIT theory is. It just crushes a problem like this. I like it. All right, so I'm going to move on to the next one. We could try another riddle.
If we didn't use DDIT, we would probably have quite a trouble doing power ratio lemma or something.
Yeah, it would probably be really, really tricky if we didn't use it. All right, so let's try another riddle. That was an easier riddle. Once you know that trick. Otherwise, yeah, it would have been super hard. All right, so we have a triangle ABC, orthocenter H and circumcenter O. Whoops. So here is the circumcenter and the orthocenter. It's that. And then OH, that's the Euler line. We want to see where it intersects BOC. And it intersects it at K. So BOC intersects AO at the dumpty point, right? So BOC, there's always, let's see how this looks. So we'll call this K. And basically, if you draw the center of the circle, it's tangent to, yeah, let me just draw the center of it. Oh, wow, you can't even see the center. Oh, no, it just didn't draw it right. So yeah, EB and EC are tangents to the circle. And then AK intersects BOC again at R. So I might have to redraw this, maybe make triangle ABC smaller. Oh, whoops. I think let me just see what happened. Whoops. Okay, so I must have renamed this D accidentally. Oh, here it says 0.0. What's going on here? So I'm gonna, what if I hide D? Let's try this. Let's see. All right. Hey, Ryan, thanks for joining us. So it looks like that worked and I successfully renamed it O. So this is our second problem. The first problem, I could show you it really quick, but there's this theorem that I didn't know about that Stefan showed me. So it's a dual Desargues involution theorem, and it just like crushed this problem really quickly. So if you ever have free time and you haven't already seen it, I would search DDIT. I'd only seen a special case of it. But yeah, this is a really fun problem. All right, so I'm going to check this out.
May I ask you, you said that EB and EC will be tangent to circle ABC?
I think so, because, oh no, they're not, my bad. I was thinking the wrong thing. All right. So let's see. We'll draw it like that for now. So AK intersects the circle at R. And the perpendicular from O to AB and AC. So I mean, basically, those lines go through the midpoints of AB and AC, right? because the perpendiculars from O go through the midpoints and they intersect BC at L and S. All right. So that would be one of the points, and this would be another one. So this is L, and this is S. Let me try hiding this and then drawing the point. I think that, there we go. We want to show RSOL is cyclic. All right.
This problem is related to discrete geometry Olympiad.
Oh, yeah?
From there, yeah.
Did you see this problem before?
Not exactly this one, but it had this point K and R.
Okay.
And that was the problem my team had 0 points on.
It was just a really hard one.
Yeah, yeah.
Right.
Even though it was problem 2 and not problem 3.
Oh, this shouldn't be S. This should be S, I think. But that it was a problem 3.
No, this was a problem 2.
Oh, interesting. Must have been really hard. Okay. Let's see. So I draw this, draw this, draw this. So thanks for joining, Roland. All right. So let's see if we can make it. I think this looks okay. Maybe we can make it look a little nicer. Maybe something like that. Okay, so we have to use somehow that H is the orthocenter. So probably we could use that, a reflection of it lies on the circle. I think that's probably the easiest way to use that. But I know there's got to be something special about the circle BOC. Like I feel like it comes up, like if you intersect the circle ADOF with the circle BOC, it's the, I think it's the A Dumpty point, right? Yeah. I don't know if there's any other thing special. So we know OB is equal to OC, and we know EB is equal to EC. So this is a kite.
Take the intersection points of BOC and AB and AC.
Okay. So
those will actually be the intersections of perpendicular bisectors. That is an angle chase to prove. So
yeah, so like these concur and these concur basically.
Yeah, and what's nice about it is that we can invert about about ABC, that circle.
Okay.
And we need to show that RS OL is cyclic. So S and L invert to J and I.
Okay.
And R inverts to intersection of RO and BC.
Okay. RO and BC.
Yeah. So we want to show that RO, BC, and IJ are concurrent.
Okay. Oh,
and this now really looks like that problem. I think in that statement we also you like intersect AO with BOC.
Okay.
And then I think we will have that K and that point also should pass through that. So
KM and N would be linear.
Yeah, yeah.
Okay.
But it was like in the problem, it wasn't stated with this Euler line. You had to notice the Euler line and some stuff after that. But this is like something which was needed to prove. I don't know how to prove it still.
Okay. All right, so it looks like we have 2 more people that joined. So thanks for joining, Nico and Khan and Wen Khan. Okay, so you did a root BC inversion followed by a reflection about the bisector?
No, just an inversion about ABC.
Okay. An inversion about ABC. And so B goes to J and I goes to C. Or no, I'm sorry. Not, that would be about A. Okay, so S goes to J and I goes to L. We crushed this one with DDIP. So yeah, that was right before this. Okay, so S and L get swapped. And that you said that's probably just a calculation. And then I and L get swapped.
You just need to show that I is actually that point on BOC. So you intersect OD with AC and prove that OICB is cyclic, and that is an angle chase.
Okay. Because, yeah, we want to show OIBC is cyclic, but we know angle BOC, that's twice angle A, and then angle BIC is, well, I mean, we know BIA is isosceles, so from there we kind of can angle chase that. I'm guessing is the idea. Interesting. Okay. So yeah, so that shows that I and J lie on that circumcircle BOC. Okay. So yeah, so we want to show K, M, and N are collinear. How do we, so yeah, K and N are kind of straightforward to define, but then M, we have to intersect AK and then intersect OR. I want to make this slightly bigger. Sorry. That looks better, I feel like. All right, so K, M, and N. Let's see. Maybe Pascal's theorem or something. Yeah, we have to use, I don't think it's enough that O and H are isogonal conjugates. I think one has to be the circumcenter, and because yeah, otherwise we couldn't do all that inversion stuff with, yeah, otherwise I wouldn't lie on the circle and all that. So I think angle DIB is C, yeah, angle DIB equals angle CIL. Because DIB is AIB, which is CIL. So yeah, those two are, IB and IC are basically like isogonal with respect to IB and IL. That makes me wonder if we can use the isogonal line limit somehow, but I'm going to hold off on that. See. One sec, I'll be right back. I'm going to get the charger from my computer. It's running low on battery. All right, looks like someone else is joining. Hey, Peter, or let's see. Hi, Peter, thanks for joining. So this is our second problem. All right. So yeah, for everyone new, if this is your first time, you can either speak out loud if you have questions or see anything, or you could type in the chat, whichever one you feel most comfortable with. See who else is on. All right. So, all right. So we could show Km and N are collinear. Let's see. Oops. Can we use Menelaus for that? So we'd want to show NO over NA times AK over KR times RM over MO is 1. It might be a little tricky. And then the other way is to show that J, M, and I are collinear. So K, M, and N, and J, M, and I. Maybe we could let IJ intersect BC at M prime, and then we want to show O, M prime, and R are collinear. I wonder if that might be easier. Yeah, the key is how, point K is defined. We're letting OH intersect the circle at K. All right. So yeah, we have to use that K lies on the Euler line.
Maybe we can try proving the concurrency with cross ratios.
Okay.
So we could try to show that BCOI is CBRJ.
CBRJ.
Yeah, and every point there is quite good for lengths apart from R.
Let's see. So CBOI, if we show that cross ratio is the same as CBRJ, then that means they're concurrent. Okay. So CBRJ, maybe we can project that through, what's a good point? So we can project it through A onto the circle, right? Yeah. Like, because you can project it through a point that's not on the circle, right? So if we project it through A, then we would basically get BBKI. So like we get a degenerate quadrilateral BBKI. Is that right?
No, I think B and J just swap. Since we have CBRJ.
Oh, B and J just swap. Okay.
Yeah, that looks really good actually.
So then we'd have BJKI. This is our second one. We solved one right before this. We used DDIT. I don't know if you've heard that, but it's a really powerful theorem, dual Desargues involution theorem.
Maybe we can now project onto the altitude through O.
AH.
Yeah. Then we basically get rid of most points in the diagram, I think.
So then we would have this point right here, right? These two.
Yeah.
And then
we also intersect BO and CO with the altitude.
All right. So K goes to H. Yeah, we'd have to intersect BO and CO with the altitude, but then we get some kind of symmetry. So that might be helpful. So POQ is isosceles. So then we would have PQ, we'd have to draw PQH in this point. Yeah. Yeah, this would be the only point that's like weird. Point T.
Point T also isn't that weird. It is the intersection of a bisector of AC, side bisector.
Okay. Yeah, that's a good point. It just lies on this. Okay, so PQHT. Okay, so just to recap, we wanted to show BC BCIO equals BCJR. BCJR, then we project through A, and we get BIJK.
Oh, this is actually not good. The projection P should be the intersection of OI.
Oh, all right.
But then it is also quite symmetric. We just have two bisectors.
Okay. Yeah, the two perpendicular bisectors. We see where they meet. So yeah, we can project those points. Maybe we could project those points through O onto DF.
Yeah, that looks good also.
So yeah, if we take the orthocenter H and we project it through O onto DF, I don't know if there's something special about this point. And then Q is where BO would intersect it. Yeah, I'm not sure how helpful this is though. BJKI. Yeah, I like projecting through O. I'm just not sure. Okay, so yeah, we take this midline and we project H onto it and B onto it. And then we want to find that cross ratio. Is there another way we can do that? Yeah, we have to use that H as the orthocenter. Let's see. So we want to show that this cross ratio is BCI. Was it BCI O? So what if we project BCI O through it? So if we projected BCI and O through O onto this line, O would go to the point at infinity. I would go to D, B would go to V, and C. I wonder if those are harmonic. Let's check. So I don't think so. But if C intersects this at point W, so yeah, we want to show that dWV infinity is like dFVU. It's like we have to use something about the orthocenter. I think that might be what's missing. Yeah, this looks a little bit messy, but I'm gonna make it look a little better. Okay. Point V. Oh, I just draw that in.
What if we project these cross ratios onto the circle ADOF instead of the line?
Ah, interesting. It seems like an interesting idea. So DNF would stay fixed. Okay, so we had BK. Was it BKO? BJ KC? BJKI, I think, right? Yeah. So BJKI, and we project through O onto the circle. So J goes to F and I goes to D. And then we want to see where B and K go. So B and K, where do they intersect that circle? Yeah, it's kind of tricky. I'd have to zoom in. Yeah, I feel like I've drawn so many points that, let's see.
I think that I, J, L, and S are cyclic, and I'm having an approach of using angles and trying to prove it like how we usually do. But yeah, I accidentally found out that JS and IL are kind of cyclic.
Okay, interesting.
That follows by the inversion, actually.
Wait, so you've proven that? You have proven that?
You just invert. Wait. What is S? S is. What point is it actually?
S is where OF intersects BC.
So is it linear with A and R?
Because if you can prove that, then it follows by an angle chase or maybe spiral similarity that RSOL must be cyclic too.
Could you just move the diagram a bit, Michael?
Okay. Oh, AS and R are not necessarily collinear. Yeah.
Yeah. That was.
That's what you were wondering.
Yeah, I mean, you can prove that the JS and L are cyclic very easily. You just invert about ABC, and that basically solves it. But I think you made a mistake while assuming
Yeah.
AS and R.
Yeah, because I didn't use point K. Yeah, it didn't finish. It just helped, but it didn't finish.
Okay.
Interesting. So yeah, let's see if I could try your idea. So we want to see where BO and KO intersect this circle. I could try zooming in a bunch. It's let's see. So BO oh no, so we want to see where KO intersects it. Oh, so BO, so it's like we have this point, Z, right? Yeah. And then KO, that's basically where HO intersects the circle. I think it's like, yeah, it almost looks tangent, but I don't think it's tangent. So let's see. Yeah, KO almost, there we go. So here you can see it. So it would be like ZA1BF. We would want to find that. Yeah, I'm not sure how much simpler that would make it. Unless we could show that that's similar, because we want to show that the cross ratio is the same as BCOI, right? So wait, is A1 the midpoint of DF? I don't think it is. But that would be very, yeah. That would be very interesting. So I guess I can try to shrink it like this. One sec, I'll be right back. All right, got some water. So we know JSIL is cyclic. We want to show RSOL is cyclic. Any other circle through S and L? Let's see. It almost looks like this is cyclic, but I don't think so.
Michael, maybe we should stop trying to be smart and just bash.
Bash, okay.
Yeah, I mean, look, instead of trying to project the BOIC, it is actually a really nice expression. You know, BO over OC is just 1, and IC over IB looks like not so good, but it is actually really good because IB is equal to IA.
Yeah.
So that expression is just IC over IA.
Okay. So that would give us BOIC, right? And then we want to show that's BCJ R, right?
Yeah, but I think it is better to work with IJKB.
IJKB, yeah. So IJKB, that's what we got after we project through A. And let's see. Or we could try projecting onto AC. Although it's not clear where K goes then.
I think that is okay, actually.
See you next time, Simon. So projecting onto AC.
I mean, that is just the intersection of Euler line and side of triangle, which is not good, but I don't think we can do much better than that.
Okay. Okay, so, and then, okay, so we would have IB1C was BJ, BJKC, and then B1CF. B1CF and what am I missing here? Just the intersection of BO with AC. Well, yeah, I think this point, right? And then, yeah, so like we could just take this point right here. So yeah, let me hide a bunch of stuff. So I'm actually going to delete this. Okay. So we'll let BO intersect it. And we'll let this intersect the side. So we want to see where the Euler line intersects the side, and we want to see where BO intersects the side. There we go. try to make it look a little nicer. It's hard to make a great diagram, but I think that looks good. Well, now FE and U are too close. Maybe that's okay. I could probably delete some of these points too. Delete that. Okay. Yeah, FE and U are kind of close together, but oh well. Yeah, what is P? Oh, is P that point up there? I think so. Okay, so we want FV FVU C. So yeah, V is the midpoint of a C, or no, F is. So FC and then VU. So we want to show that that's BC IO. So yeah, FVIC we want to show FVIC is BOIC. Wait. Yeah, now I'm just confused. No, BJKI. No, F. We want to show FIUV. I keep getting confused. FVUI. We want to show that is equal to BOIC. Sorry, I'm going to be back one more time. I have to do something. All right. Thanks, everyone, for waiting. Sorry about that. Let's see. So it's 10:13. So we can work on this for maybe another 5 minutes or so, and then maybe move on to the next one. Unless we find something big. So yeah, we want to show these concur. These concur. Yeah, I'm not sure how to get the intersection of OH with AC. Oops. Let's see. Let's see. JBKI. We let RS and RL meet the circle at Y and X. Okay, so I, Y. Okay, so by symmetry, we could basically just do one of them. So it suffices to show that IY is parallel to BC. Wait, really? Because IY has nothing to do with, does it have anything to do with point? Oh yeah, it does. This R is defined based on K, which is defined based on H. So we want to show RS and RM are isogonal. And similarly, we want to show RJ and RL are isogonal. I wonder if RJB is similar to RCL. Yeah, I think RJB and RCL are similar. Is that obvious? Well, it's obvious that one of the angles are equal. I think that might not be so hard to prove.
Proving the similarity is equivalent to the problem, I think.
Oh, really? Okay.
Yeah, we can ignore everything we've done before and just angle trace after, if we prove the similarity.
Okay. So RJB and RCL and J and L. Okay, so J is the intersection of AB with that circle, and L is the intersection of ID with BC. Maybe we could use the isogonal line lemma. Actually, I'm not so sure about that. It's more like a spiral similarity. So it's basically saying there's like a spiral similarity from. So RBJ is Yeah, so there's just something special about this point R where, yeah, RBJ is similar to RCL. And it looks like so is there another angle? Can we show JBR is CLR? I wonder if AJ and RL meet on the circle. Okay, it doesn't look like it. Yeah. All right. So yeah, we have one of the angles are equal. Let's see, RBJ. So we want to show our angle RCJ is RLC. So RBJ is RKJ. All right, I think I'm going to go on to the next problem and then we can go back to this later. My brain is just tired of all the cross ratios and everything. But I think we're close. All right, let's see. This one I think might be easier. So let's see how we can do on this one. So we have a quadrilateral. So we have side BC. So actually what I'm going to do, here's what I'm going to do. I'm going to rename this C and then draw two circles. So this one looks like it might be really easy, but I don't know. So CA is equal to BD. Wait a sec. So this could be A, and that could be B. Okay. And then M and N are the midpoints of AB and CD. I guess I might as well draw this and this, right? Okay, so those are basically the phi to the altitudes from C to AB and B to CD, so M and N. And MN intersects BD and AC at T and R. So this is R. And this is T. And we want to show that BT plus CR is BC. Okay, so let's make this a little bigger. And try not to make it too much like a trapezoid. I think that looks good. So obviously BN is the foot of the altitude here, and CM is the foot of the altitude, because these are isosceles triangles. Now we could check that problem's actually true.
Oh, intersect AC and BD.
Okay.
There is this lemma called the Sparrow lemma, which states that BT plus CR is equal to BC if and only if a circumcircle of ETR passes through the incenter of EBC.
ETR passes through the incenter of
ABC, and it looks like it may be that point.
It is that point, because these are both angle bisectors.
Okay, then we need to show that.
Okay.
This is cyclic. This is actually not hard to prove. I mean, it has an interesting proof, but it is mostly angle chasing, I think. There is nothing
really?
like hard in that proof.
Okay. So we want to show this is cyclic. So yeah, we know this is the incenter. Let's see. So yeah, this is an angle bisector right here. So really we want to show that, I think if we show that ET equals ER, that might be good enough. I wonder, I don't think these are the FT and FR. Maybe they are the phi to the altitudes from F to the two sides. Oh yeah, it looks like they are. Is that obvious? So F is the incenter of EBC.
Oh, I think it is. This is by iron lemma, right?
Oh, yeah.
D is like the reflection of C over bisector, and also A.
Okay. So basically by the Iran lemma, if we reflect C over the bisector, or if we draw the perpendicular, I know if we draw the perpendicular from C to the bisector, then the theta, the altitudes, or the, yeah, so the points of tangency, if you draw it, it passes through that point. And then the same thing is true with point M. So MN would have to pass through the 2 theta altitude. So yeah, T and R are the theta altitudes by the Iran lemma. So therefore, this is the incircle. And then by the lemma that you said,
You don't even need that lemma now.
Oh, really?
It's just,
yeah, it's just this. Yeah, it's trivial. Okay. So yeah, this one was too easy. I'm gonna write it up quick. But yeah, so I'll say draw the incircle of EBC. So first of all, I'm going to show that F is the incenter. So let Bn intersect Cm at F. Then by symmetry, Bn and Cm are angle bisectors of EBC. And that means that F is the incenter of triangle EBC. And then once we know that, let the incircle be tangent at R prime and T prime. By the Iran lemma, N, R prime, and T prime are collinear. So are M prime, M, R prime, and T prime. So. And then that, so that means that R prime equals R and T prime equals T. And then once we know that, so BT equals BG and CR equals CG. So BT plus CR equals BG plus CG equals BC. Okay, so yeah, a lot easier than the last one. All right. So let's see where we can go now. Yeah, it's yeah, sometimes that button to minimize the screen doesn't work.